Okay, welcome back, everybody. Let me do a quick fix here. All right, hope everybody had a good weekend. I don't have anything to announce, so unless there's a question or anything that you need, let me continue with chapter 5. We'll be done with that, and we'll probably be pretty close to done with chapter 6. It's pretty short because we're only on chapter 5. We're on slide 31. So. Okay, if there are not any questions, oh yeah, I do apologize. No, wrong class, sorry. Let me continue, never mind. Okay, well, let me share the slide that where we left off. And we were in slide 31. We've been talking about the electron configuration, okay? Now, what that is how do we display the energy levels that these electrons occupy with respect to the elements, okay? There are 7 energy levels. We talked at length about that, which is related to the 7 periods on the periodic table, energy 1 level to number 7. Within these energy levels, there are sublevels noted as orbits, which are mathematical models that display where an electron is, or the probability of electron being in, hold on, I'm getting my internet telling me it's unstable. Okay, well, so we have these orbits that tell us where the probability of an electron being. There are 4 orbits, denoted by the letter S, P, D, and F. And for the S orbit, there's only 1 S orbit. For the P orbit, there are a total of, there's 3 orbits. For the D, there are 5. And for the F, there are 7. Okay. And then we talked about each orbit or orbital can handle a maximum of 2 electrons. So the maximum number of electrons in an S orbit can handle is 2. The maximum number of electrons in the P orbits, all 3 of them can handle, is 6, 2 per each one. And the D's total is 10 and 14 for the F. Okay. We can utilize a periodic table to help us write the electron configuration, where you show the number, which that coefficient up front is the energy level. If you look at that image on the right side, on the very first column, you see the coefficient 1, 2, 3, 4, 5, 6, 7. That represents the different energy levels. Okay. And then if you note that in the first 2 columns, those are, we talked about this, think of those as the S electrons. And notice that these are the S electrons, and that when element number, let's say this element here, well, its S electron is in the 2s1. The superscript represents the number of electrons for that orbit. You move over to the next element, which here is beryllium, and then its outermost shell. Let me back up for a second to make sure we're on the same page. That if I'm looking here at beryllium, and beryllium occupies the 1 and the 2nd energy level. Okay, so beryllium, everybody in that 2nd period has 2 energy levels. That's it. Okay, and it's 2 electrons in the outermost shell, which we call valence electrons, occupy the 2s2. Now we shoot across over here to boron. You can notice that we go from P1 to P6 as we go across the periodic table. So that's 6 columns that represents the P elements, okay? Then we come down here to the blue area, which now begins with the D elements. And so if we look at this one here, which is element number 21, and only when elements number 21 come into play and up, that you start picking up the D elements. okay? And we are going to just say from first column D1 to D10, all across the board. Yes, they hop around, but for us, we're just going to say, if we have to pick, say that element, that would be D3, D5. Now, the energy level for those elements, for that number 21, let me clear it up a little bit right here. That's where the D orbitals come into play. But, and even though it is in the fourth energy level, okay, here, listen carefully. Starting for this one here, this is element number 21, the D electrons begin. Okay, as we start to fill up the D orbitals. But the D orbitals for that element right there, which is number 21, do not begin on the fourth energy level, but actually begin one energy level in from what it's at. So you can see that here, the D start off at 3D1, okay? The one below number 21, its D orbitals begin in the fourth energy level. They're one energy level. So for the D, the energy level they're in, it is one, the energy level they're in minus one, okay? And so we can say n minus one, n represents the energy level that those elements are in. When we get down to the F, okay, the F would be 4, 5, 6, and 7 would be in the 6 and 7 energy levels. Now, for the Fs, for the F orbits, these are the Ds, okay, for the F orbits, they start to come into play 2 energy levels in from where the energy level that element is at. And that's why for this one here, the F orbits are in the 4th energy level and not the 6th energy level, okay? But that's only for the Ds and the F. The S and the Ps, whatever period they're in, whatever energy level they're in, that's the energy level that those particular orbits are in, okay? So I prefer to use the periodic table and the position of the element, and we're going to do some examples of that. Or you can use the scale or the sequence that, where is it? There it is right here. We use that sequence given 1s2, 2s2, 2p3, etc., etc. Either one will work, like I stated, but I prefer the periodic table itself. Okay. All right, so here we are. So when we talk about the valence electrons, keep in mind, we are talking about the electrons in the outermost energy level. And so if we look at phosphorus in here, there are, if we do the electron configuration for phosphorus, it is 1s2, 2s2, 2p6, 3s2, 3p6, okay? Excuse me, 3p3, which is right here. Here's phosphorus right here, is in the 1, 2, 3 energy level, okay? So we know that the first energy level is full, which is right there. We know the second energy level is full of its electrons, which are these two right here. Check that out. And then we know that it's in the third energy level. So here comes the S electrons, which is there. And then we know that phosphorus is 3 columns in the P from the left, 1, 2, and 3, which tells you how many electrons are in the P orbit, which is 3p3. Okay, see how that works real well? Hopefully. Now, also, if you look at the Roman numeral on top, it should list as 5a for that particular column. So if you look at your periodic table, phosphorus is in the group labeled 5a. That means that everybody in that group has 5 valence electrons, okay? Now, those valence electrons will be in a different energy level, but they all have 5 valence electrons. And so below phosphorus is arsenic, which is right there. Okay, its 5 valence electrons are in the 4th energy level, whereas the 5 valence electrons for phosphorus are in the 3rd energy level, and above phosphorus is nitrogen. It also has 5 valence electrons, but they are in the 2nd energy level. Okay, and so they fit nicely because they're on the same group, which also tells you the fact that they have 5 valence electrons. They're going to react very similar. Okay, so the other takeaway from this is, let me clear this up a little bit. Seen from its electron configuration, that in the p orbit, there's still room for 3 more electrons. Remember, the p's, all 3 p's can handle 2 electrons, so a total of 6. So the p orbits can pick up 3 more. Now, phosphorus is a non-metal. And like I stated, I told you before, think all non-metals, they gain electrons. And they gain electrons, why? Because they have room. It's easier to pick up 3 electrons than to try to get rid of 5, these 5 that I circled. Okay, so from an energy perspective, pick up 3 instead of trying to take out 5 of them. It's going to be a little more difficult. And when it does that, those 3 electrons that it picks up are going to occupy those empty orbitals in the p. And so now, by picking up 3 electrons, 3 is 2, 3, p, 6, okay? Phosphorus has a net charge of a -3. This is phosphorus, the element down here. And the one above I just wrote, that's the electron configuration for phosphide. We changed the name for phosphorus from phosphorus to phosphide when it picks up 3 electrons. And it does that because it has room for it. And also it is a non-metal, okay? And now when it picks up 3 electrons, it has the same number of valence electrons as the noble gas in front of it, which is, guess what? Argon. I didn't say that the phosphide is argon. I said was this, that the phosphide ion, in picking up 3 electrons, now has the same number of total electrons as argon. And argon is in this last group that, guess what, has that magical 8 electrons in the outermost shell. Phosphide now has 8 valence electrons in its outermost shell, okay, and therefore a lot more stable than phosphorus itself. And finally, the final aspect about valence electrons, that is where all the chemistry happens. That's where all the actions happen, the valence electrons. All right, so you may be asked to determine, well, what is the number of valence electrons, okay? Be careful to discern the difference between the total number of electrons and the valence electrons. We're not concerned about the total number of electrons. We want to just know how many valence electrons it has. And to do that, you find the element on the periodic table. And we can only do this for the ones that have a Roman numeral A, what we call, right now I'm calling them the A elements, okay? The other ones which are labeled with the B are unpredictable, and it's difficult to determine how many valence electrons they may have. So for the A only, I look for chlorine on the periodic table. And you could do this a number of ways. You could find its position, its position in the periodic table, and find what group it's in by simply going up to the top. And you will notice that chlorine is in group 7A, Roman numeral 7A, which tells you that you have 7 valence electrons. And those valence electrons are in the 3rd energy level. 5 of them are in the P, 2 of them are in the S, okay? Beryllium, if you find beryllium, it's number 4. Chlorine is number 17. Beryllium is number 4. Aluminum is number 13, element that is, okay? And beryllium is in group 2A. So I can very quickly tell you that it has 2 valence electrons. But if you don't know, write the electron configuration for it. And its 2 valence electrons are in the 2nd energy level. And they occupy the S orbit of the 2nd energy level. So it's 2s2, okay? Then finally, aluminum is in group 3, Roman numeral 3A, which tells you it has 3 valence electrons. And in doing the electron configuration, you'll see that those 3 electrons are in the 3rd energy level, which 2 of them are in the S orbit and 1 of them is in the P orbit, okay? Now, as we just talked about a minute ago about phosphorus, where it gained electrons because it had room to put in 3 electrons, and it was much from an energy perspective easier to gain 3 than to lose 5. Here, there's 3 valence electrons in the outermost shell. And to gain 5 is a lot more challenging here than to lose 3. Aluminum is a metal, and like I stated before, all metals, put this in long-term memory, all metals lose electrons. And in doing so, it will end up with a +3 charge because it lost 3 electrons. And its electron configuration now is 2s2, 2p6. Its new valence shell, which is in the 2nd energy level, has 8 electrons. Very similar to the noble gas behind aluminum, which is neon. You see the trend here? When it's a non-metal in gaining electrons, they gain the same number of electrons as the noble gas in front of it. When it is a metal and they lose electrons, they then obtain the electron configuration of the noble gas behind it, okay? The ultimate goal, either in front of you or behind you, is to get that magical 8, and that's what's happening here. That is the driving force of creating what we call the ions, either the negative ions or positive ions. Okay, so looking at the Roman numeral, that corresponds to the number of valence electrons for the A element. So it's shown here. 1A is 1 valence electron all the way down across the board to Roman numeral 8A, which has 8 valence electrons. Now here's something to note. This is the pivotal point at this group 4, okay? So on group 4, of which carbon is in that group, okay, they are on the fence. Think of it as being on the fence. And depending on the reaction conditions and so forth, those guys and those elements in group 4 can either gain 4 electrons or lose those 4, okay? Because from an energy perspective, yeah, the number is the same, 4. Lose 4, gain 4, about the same, right? So they can have a charge, overall charge after that happens, of all the way from a +4 to a -4, depending on how many electrons they lose, okay? Now, the groups before groups 1, 2, and 3 are all metals. And what they're going to do is they're going to lose those electrons. Specifically, lose one for the group 1A, which gives them a +1, +2 when they lose the 2 electrons for the elements in group 2A, and for the elements in 3A, the metals specifically, they end up with a +3 charge. These are the ions that are being created by losing those valence electrons, okay? For the nonmetals after group 4, starting in group 5, okay, now they're getting closer toward the noble gas in front of them. And these are nonmetals, and they're going to gain electrons. And the number of electrons they're going to gain depends on what group they're in to get that magical 8. So group 5, they're going to pick up 3 electrons, which gives them a -3 charge. Okay. Group 6 is going to pick up 2 electrons, which gives those elements a -2 charge. Okay. And then the ones in group 7A are going to pick up 1 electron. By picking up 1 electron, they get to that magical 8. Okay. By losing it 1, 2, or 3 electrons, they also get to the magical 8, but to the noble gas behind. Okay. So hopefully that gives you a better picture when we start talking about compounds and then what kind of charge they have, because we're going to learn about these ions and then be able to put them together with respect to the charge that they have. Okay? But we need to know what kind of charge they're going to have to begin with before we can put them together to make any type of compound. Okay. The only exception is helium, and real straightforward. Its magical number is 2. It's the duet. It only has 2 valence electrons. All right, so in this scenario, they're giving you all these elements, and you simply need to go to find them on the periodic table, determine what group they're in, okay? And that information tells you how many valence electrons. So strontium is in group 2A. Okay. Bromine is in group 7A. Argon is in group 8A. Silicon is in group 4A, Roman numeral 4. And sulfur is in group 6A. Okay. And that gives me that information as far as how many valence electrons they have. Okay. Knowing that then helps me determine what their charge will be when they get converted to ions. All right. So, why do atoms make compounds? And that is because the ultimate goal is, like I stated, is to get to that magical 8. Now, there's 2 types of compounds that we're going to make, 2 types of bonds. We're going to make ionic bonds, which basically, they have a full negative charge, full positive charge or full negative charge. And they come together much like 2 magnets come together because the opposites attract north and south, and they have this attraction. Well, the positive ion became positive because it lost electrons. The negative element gained electrons and it became negative, okay, to form what we call ionic compounds. The other type of compound that we're going to talk about are molecular compounds, where they're not having a full charge like ionic compounds. They have a partial charge, but nevertheless, they're going to share these electrons. And in sharing, they're going to have 80 electrons around it at all times, bonded, okay? Except for hydrogen, we'll only have 2. But again, the goal in both types of compounds is to get that octet, okay? So first, let's talk about, which we did already, talked about making ions. We note here that sodium has 11 protons. Its electron configuration is 1s2, 2s2, 2p6, and the valence shell is at 3s1, okay? It is a metal, and it will lose that one electron on the outermost shell. So now its electron configuration is 1s2, 2s2, 2p6, plus we have a charge on it. They have a charge of +1. Why? Think about this from a mathematical standpoint. There are 11 pluses and there are now 11 negatives. In the beginning, there was 11 pluses and 11 negatives. Balance it out. 11 positives cancel the negative on the 11 negatives, we get a net 0. But now we got 11 positives. That didn't change, right? What did change the number of electrons. And so 10 of the positives cancel out the 10 negatives, and we have a leftover 1 positive. So we end up with a +1 ion charge, okay? That's how we end up with that charge. Be careful that this is the element. This is the ion, and not to forget to add the charge. Now, sometimes you see it with a +1, but there's nothing wrong when it's just a 1 to just put a plus symbol. I generally put a circle around it, and for me, I just out of habit, I've been doing it so long. When I see a charge, I put a circle around it to remind me that's a charge, okay? And there's no question about it. And also put it up in the superscript area. Okay, that is a positive example. But we also have negative examples in nonmetals. We got sulfur with 16 protons and 16 electrons with a net 0. Okay. You can see the electron configuration here. It is 1s2, 2s2, 2p6, 3s2, 3p4. The third energy level is the valence shell. Sulfur is a nonmetal. It's going to gain electrons. Okay, because it has, it's a nonmetal with gaining electrons, plus specifically, it's going to gain 2 electrons because there's an empty spot in the p orbit for 2 electrons, and that's where they go. The result is now we got 16 protons, and now we have 18 electrons. So the 16 positives and 18 negatives. And so we have a net of a -1, okay? Excuse me, -2, excuse me. Don't forget the charge can vary from -1 to -3. It depends on how many electrons they gained. Same is true for metals. They can range from a +1 to a +3. The ones in group 4 are the ones on the fence. Depends on the conditions. Could be a +4, or it can be all the way to a -4 in that whole range, in any combination thereof within that range. All right, let's clear this up here. All right, so in here, they're asking you to write the electron configurations. When you see that, don't be confused with it. Make sure that you are talking about the element versus the ion. Okay, see, here we have the element on the left side, and on the right side, we have the ion. So don't present the element electron configuration for the ion electron configuration, because it's not correct. So we have here 1s2, 2s2, 2p6, 3s2, 3p6. Now, what a lot of students do to help them out, to keep follow through, is they write the electron configuration for the element, okay, which is similar to the ion. Oh, excuse me, that's 3p6, and then potassium is in 4s1. Okay, so that is the valence shell, valence electron for the potassium element. and it is in group 1A, so it's going to lose 1 electron, specifically lose that one to form the potassium +1. And now its new electron configuration is in the 3rd energy level, and it has 8 valence electrons, which makes it stable. And its electron configuration is like argon, okay? Like argon. I can't overemphasize that I did say that the potassium ion is argon, okay? Because in order for potassium to become argon, what must happen? What must happen for potassium to actually become argon? Anybody have an idea? Argon's number 18, potassium's number 19. What must happen for potassium to become argon? What we got here? Not quite. Can't lose an electron. Remember, we can lose protons and neutrons all day long, lose and gain them. But we never lose what that element is unless what? We lose or gain what defines an element. Of the 3 subatomic particles, what defines an element? The proton, the neutron, or the electron? It gains, 3 protons. Not quite 3. Remember, but you're correct, Jessica, it will gain a proton or lose a proton. But for potassium, okay, for potassium, which has how many protons does potassium have? 19, exactly. How many protons does, where is that, argon have? 18, exactly. Yeah, you were looking, yeah, Jessica, you were thinking of electrons on nitrogen. And so when I say that, what did I do? There it is. When I say that potassium ion now has the same number of electrons as argon, I'm not saying that potassium ion is argon, okay? Because in order for that to happen, this potassium would have to lose 1 proton to create a whole new element. Okay? The only thing it lost was an electron. So now it shares the same number of electrons as argon. All right. All right, so now we have the electron configuration for N-3. Remember, it's nitrogen in group 5A. Okay, it's a nonmetal. It will pick up 3 electrons, resulting in a -3 charge. Okay, and now it has the same number of electrons as neon. Okay, again, it has the same number of electrons as neon. It's not neon, but they share the same number of electrons. And then we got magnesium, which is element number 12. It's a metal. It will lose those 2 electrons. So now its configuration now is like neon. By losing 2 electrons, okay, it got rid of them. It now has an electron configuration of 1s2, 2s2, 2p6, which is the same electron configuration as the nitrogen ion, which, by the way, we changed the name to nitride. Okay, when nonmetals, single nonmetal elements become ions, we change the name with the suffix of IDE. So oxygen becomes oxide, sulfur becomes sulfide, nitrogen becomes nitride. Okay. Potassium, all we do is still call it potassium, but we just add the name ion. The potassium ion versus the potassium element. That's how we distinguish between the two. There's no name change for the metals. There is a name change for the nonmetals. Okay. And you might say, well, why is that important? Because you may have something like, okay, you have the formula potassium nitride. And what they want you to do is to write the formula for potassium nitride. Okay. The fact that you have a metal and a non-metal combination tells you a couple bits of information, but the first thing you do is you convert the potassium to the ion, and you have to know what group it's in. Potassium is in group 1, so automatically that tells you this is a +1 charge. You look for nitrogen, it's going to gain 3 electrons, so it results in the N-3 charge. Okay, so now I start with the name, I convert them into the ions. Now I can put them together, and the way I put them together is that I put enough positives and enough negatives together such that they cancel each other out. So that means I need 3 potassium ions for every 1 nitride. So that 3 becomes a subscript for potassium. So the formula for potassium nitride becomes A subscript 3N. Okay. And you might be asked to go in both directions, meaning if I have the formula, give me the name. And if I have the name, give me the formula. Okay. And if I have the name, I have to convert them first into ions. And to know that, to know what ions they are, I got to go back to the group that they're in to determine whether they gain electrons or lost electrons. And that tells me what kind of charge they have. Okay. All right. So here is basically the group number and what is their charge and the point. Here is just a rehash of what we just talked about. The group 1A metals, by losing 1 electron, they're going to be like the noble gas behind it. Okay. And the same with group 2A. All right. So, and then also when losing those valence electrons, you have their respective charge, +1, +2, +3. Okay. Now you can write it either way, either +2 or 2+, makes no difference how you write it. It's the same thing. All right. And it's not necessary if it's a single charge to just leave it potassium plus like here, or if it's a single negative, to leave it as chloride negative charge like that. That's fine. You don't have to put a -1. If you do, that's fine too. But if you don't, that's all right. Either one's correct. But the thing to remember is there's superscript on the right side, superscript, the charges are. All right, this again is the anions, group 7, they're going to become -1, group 6 be -2, okay? And it's because nonmetals want to gain electrons. And here we introduce their specific name, and that is the name of an anion. And so when you hear the term anion, you are talking about nonmetals that become ions. Okay, so the sulfide and the oxide, those are anions. All right, so here's the negative charge. I did okay, metals want to lose electrons, and we got through that, but their specific name is cations. Okay, so cations have a positive charge and anions have a negative charge. Okay, regardless of the magnitude of the charge. That's their specific name to distinguish. Together, in general, they're just called ions. You have negative ions or positive ions. But specifically, when we talk about cations, we're talking about positive ions. When we say the term anions, we're talking about negative ions, which are nonmetals for anions and metals for cations. Okay. All right, this is a rehash of group 4 where carbon is. They're on the fence. They can lose or gain electrons depending on the conditions, so they can have a charge range of a +4 to a -4. Okay, and obviously group 8, they're the noble gases. They're stable. They're not gonna do anything. They have no charge there. Okay, and that is their respective charge across the periodic table, specifically only for the A elements. Okay, for the A only. All right, so what do we determine here? Well, they're asking you what charge ion would they become? Okay. So to answer this is, straightforward, hopefully. Metals become positive, non-metals become negative, okay? So we identified lithium as a metal. So right now we're not worried about the magnitude. We just want to make sure we're going to classify as either a cation or an anion. So positive for cation, lithium. Magnesium is a metal, also positive, okay? And then sulfur, bromine, and nitrogen are all nonmetals. So they're going to end up with a negative charge. Again, we're not working on the magnitude right now. We just want to identify what type of charge they're going to have based on metal and non-metal. And then finally, aluminum, which is a metal. Now, if you forget that, go back to the slide that had the breakup of metals, non-metals, and metalloids. Okay, and that'll help you out. And remember that stair step will tell you to the left of the stair step are metals, with the exception of hydrogen. It's in the top left corner. And then to the right of the stair step are the non-metals. Okay, so once we identify that, to identify the magnitude is we find them on the product table and see what group they're in. Lithium is in group 1A, so it will end up with a +1 metal, +1 charge, which is obviously cation specifically. Magnesium is in group 2A, so it would have a +2 charge. Sulfur will pick up, it's in group 6, so it would, group 6A, so it will pick up 2 electrons because it's a nonmetal, and will end up with a magnitude of a -2. Bromine is in group 7, just needs 1 electron. So now has a net of -1 charge. Nitrogen, we talked about that one, has group 5 will pick up 3 electrons. It's a non-metal. So it ends up with a -3 charge. And then aluminum is the metal, will have a plus, but it's in group 3A. So it would lose 3 electrons. Okay. Now, some additional stuff here. The name for the ions for the metals remains the same: lithium ion, magnesium ion, aluminum ion. Okay, sulfur becomes sulfide, name-wise. Bromine became a bromide, and nitrogen became nitride. Okay. Now the other aspect is this. You can start putting these guys together, plus and negatives, because that's how we're going to make compounds. We're not going to put together 2 positives and 2 negatives. They repel each other. What comes together are the positive and negatives. So you can start building up a quick database of a couple hundred different compounds, because hopefully you can see here that the lithium and the say sulfide will be one combination. The positive lithium, the negative sulfide, okay? It also can team up with the bromide and the nitride, okay? The magnesium can do the same, magnesium with the sulfide, magnesium with the bromide, magnesium with the nitrogen, and guess what? The aluminum 2 with the nitride, aluminum with the bromide, aluminum with the sulfide. So already you got 9 new compounds that you can start putting together. So lithium sulfide, lithium bromide, lithium nitride, magnesium sulfide, magnesium bromide, magnesium nitride, aluminum sulfide, aluminum bromide, aluminum nitride. Now, we put them together such that the charges cancel each other out. You can see here that we got a 2 to 3 relationship at times and not a 1 to 1. We'll get to that in a bit here. Okay, but right now I just want you to identify that's how we start putting compounds. Now, more importantly than that is these type of compounds are called ionic compounds. Okay, because they are the coming together of ions, specifically a metal and non-metal combination. There's only 2 types of compounds we're going to talk about: ionic compounds and covalent compounds. Ionic compounds are defined as a combination of a metal and a non-metal, whereas covalent compounds or molecular compounds are a combination of non-metals. We'll get some of that more in a bit. Okay, so I'm trying to introduce you to, we start off with the elements. Now we're learning about how they become ions. And then now we're going to start putting them together to make compounds. Eventually, these compounds are going to start reacting with other compounds to form chemical reactions. Okay, sort of like learning a language. You start with the alphabet and then work your way up. From the alphabet, you write words. From words, you got sentences. Sentences, you got paragraphs. Paragraphs, you got books. Okay, so when we were showing how an element loses electrons to become, they have the same number of a noble gas either in front of it or behind it, we use the term isoelectronic. Okay, isoelectronic right here. Isoelectronic tells you iso meaning the same, electronic meaning comes from the word to describe electrons. They have the same number of electrons. So that's what it's. The term isoelectronic is used. So, for example, if we write the electron configuration, which we did earlier for the magnesium ion, it has the same electron configuration as neon. Okay, so the magnesium ion, the cation, is isoelectronic with neon because they share the same number of electrons. Okay, so they share the same number of electrons. So they're not sharing protons, same number of protons, different number of protons. Now, with respect to the phosphide, the pH 3, notice I changed the name to phosphide, came from phosphorus, same group as nitrogen was, formed in a N3 nitride. It is in the same electron configuration as argon. So the phosphide ion is isoelectronic with argon. Okay. So in this particular table, what they're asking you to do is determine the electron configuration of these following ions. And so, and then determine who are they isoelectronic. And so if you look at the calcium ion, okay, that's your given electron configuration. See, normally the calcium element 6, 3s2, 3p6, guess what? 4s2. Okay, that is the element. So here's the valence shell. Some metal's going to lose electrons. It's going to have a +2 charge. And then now its mu valence shell is in the third energy level, which now contains 8 electrons. Okay, 8 electrons makes it much more stable. And that is isoelectronic with argon. We can go with the same exercise with oxygen. Note that it picks up, it's a non-metal, picks up 2 electrons, it becomes an anion. Its electron configuration is 1s2, 2s2, 2p6. It has 8 electrons around the second energy level, the valence shell, and it is isoelectronic with neon. And then chloride is isoelectronic with argon, and the aluminum ion is isoelectronic with neon. Okay. Continue with, okay, we can start mixing and matching positive cations and anions. So I can eventually combine the aluminum with the chloride and also create aluminum oxide. So I can create aluminum chloride, aluminum oxide, or I can take calcium, make calcium oxide, or I can make calcium chloride. Okay. So I'm picking up a few more compounds here that I can mix and match with. So you're going to find that all of the metals that are made into anions that you work with, I can mix and match with all the non-metals that have a negative charge. And I can just create a few hundred different compounds. Okay. And your database should add up to about, I don't know, 200-300 compounds already. Okay, so here, what they're asking you here to determine the number of protons, electrons, and neutrons. Okay, the first column you have selenium 78, and then you have selenium -2. Well, if you look for selenium, it is element number 34. Okay, so let me help you out here. Number 34. And aluminum is number 13. We're dealing with aluminum 27 and aluminum 13, excuse me. And so selenium is in group 6A. It is right underneath sulfur. So it would also, being a non-metal, will pick up 2 electrons and have a -2 charge. So it's now called selenium. Okay. And so we need to know how many protons it has. And so for Se, it's 34 protons, right? 34 protons, whether it is the element or the ion or anion, okay? It's going to have the same number of neutrons. Nothing's changed. What has changed is the number of electrons. It picked up 2 electrons to give you a total of 36, giving us a net charge of a -2. All right. Aluminum has 13 protons, be it the element, be it the ion. It has, to begin with, 13, it will have 14 neutrons in both cases. Where they differ is the number of electrons. Here, it lost -3 electrons. Here, it gained 2 electrons, plus 2 electrons. Okay. And hence the positive charge for the ion, excuse me. Okay, well, that, ladies and gentlemen, ends chapter 5. Okay. Take this home and digest it and sink it all in, and we will, come Thursday, you have any questions, come Thursday with some questions if you have anything concerning this particular chapter. Okay. Unless you have a question now. If not, I will jump into the periodic table, chapter 6. Which is fairly short, and a lot of this, again, I started to introduce you to this. So You'll be somewhat familiar. Okay. Anyway, any questions? We got a few minutes here, about 15 minutes. If probably get about halfway done with this. All right. Well, let me introduce you to this gentleman here. All right. Dmitry Mendeleev, Russian scientist, 1863. He is credited with putting together the first periodic table. And the way he did, he arranged them in order of increasing mass. And he also started to put elements with similar properties in the same column. Keep in mind, this is 1869, way before the model we have now, way before the model of having valence electrons and putting them in the same column, because those elements had similar reactivity. We now know that's because they have similar number of valence electrons. Okay. He also had a lot of holes in his empty slots in his table, which he predicted would be other elements. And sure enough, other scientists jumped in there and were discovering elements left and right based on his initial periodic table, because he predicted that there should be element X here. Okay. And what amazes me about all this is, keep in mind 1869, with respect to, the type of equipment they had to work with. A lot of this was the powers of observation and deductive thinking. All right, so Mendeleev, Dmitry Mendeleev. Forget what year, but a scientist by the name of Moseley, he put together the table based on increasing atomic numbers. Okay. And he introduced what's called the periodic law, that elements in the same column have similar properties, which we know now has to do with the number of valence electrons that they have. Okay. Very similar properties. Now, the table we utilize is kind of shrunk together, kind of brought together, because if you might wonder, well, wait a minute, why does it look so different? Well, if we look at these groups right here, which they have their own little name right here, the lanthanides and the actinides, they actually belong in here. Notice there's 58, and then it should kick in the 57, and then go to 58. Well, what was happening is the periodic table was if you split it apart and then insert these two rows, you now have a periodic table, which is the long version. Let me clear this up in this next slide. Okay, so those are the two that are kind of where they belong normally, but because of the size of it, they just take them out and put it in this format down at the bottom. There is a new naming sequence, which, pros and cons with anything new, but each column, starting with Roman numeral 1A, gives it a number 1, and it goes all the way across to 18. Okay. This is V8A, that column. Pros and cons. Here are the S electrons here. These are the F elements, S, the first two columns, then the D, and then the P's. Okay. So that's kind of a expanded version of the product table. And there's been a variety of other alternatives out there. Here's a circular product table that's been brought out to be used. It hasn't caught on very well. I think most scientists stick with the periodic table that we have. Here's another one, very interesting one, because it also predicts a lot of new elements on here, specifically up in this region. We call them the superactinides. Those we haven't been created. We're up to 118, and some scientists, last report I read, we're pretty close to about 120, 119, somewhere around there. But we'll see. Okay, keep in mind those are radioactive and not very stable, and takes a lot of energy to get them together. All right, but we generally stick to the one that we've been using. Okay, this is where Niels Bohr introduced the idea of the energy levels, and then this is where we talk about the S elements, or the S block, the first two columns, the D block, the P block, and the F block elements. Okay. All right, so the horizontal row, which is I've noted as the energy level 1 through 7, that is denoted as period. The period 1, period 2, period 3, period 4, etc. to period 7. Okay. The vertical columns are called the groups. You also may see the term family when they belong in the same family. But group is the one. The name group is the one most commonly used. Okay. Now, elements of the same group exhibit the same properties, obviously, because they have the same number of valence electrons. Now, all the Roman numerals, what I've been calling the A elements, those have a specific name called the main group elements. Okay, that's from Roman numeral 1A to Roman numeral 8A. The B group, which is really the D block, okay, are called transition metals. Okay, so we got main group elements, and then we have transition metals. So the periods represent the different energy levels or shells, and the vertical columns are called groups or called family. Okay, and again, very similar in reactivity, simply because the number of valence electrons. Okay, now some elements, some in certain groups have their own specific name. Okay, group 1A, it's these elements in the very first column, with the exception of hydrogen. Hydrogen's not that, because hydrogen is not a metal. They have their own little name called the alkali metals. Okay, alkali metals. And then the next group in, the 2A groups, they call those, their alternative name, or specific name, I should say, is the alkaline earth metals. Okay. The group 7A have their own little name called the halogens. Halogens, that's the fluorine, the chlorine, the bromine, the iodine. And we already introduced as 8A, which those are called the noble gases. Okay. Halogens you may be familiar with. A lot of old headlights have called halogen lamps. Very bright lamps. Okay. Now, the group B's are called the transition metals. Okay. So that's the ones in green. They're not very predictable with respect to the properties, because they do vary quite a bit, and there's different types. Whereas group 1A, group 2A, we know 100% that they have a specific charge. These guys in here can vary. For example, there are 2 types of copper. There's a copper plus and a copper plus 2. It depends on losing 1 electron or 2 electrons, and they vary. So, all right, now, those are the transition metals. Now, the 2 periods in the bottom are called, the alternative name is the inner transition metal. And then a more specific name, you see at the left, they call the lanthanide series and the actinide series. Okay. The lanthanide series, which are right here, you may hear them called as rare earth metals. Okay. And then literally literally all the actinide series down here, literally all radioactive material. And you can notice their atomic weight is in parentheses. In fact, anything greater than equal to 93, element 93, are all man-made and very radioactive. And they put them in these particle accelerators to make them. Okay. So, man-made elements. And like I stated, there are a group of scientists that are still working to make elements greater than 118. Okay, so with that information, you could be asked questions like, all right, what is an alkali metal in the third period? All right, so we got to find the alkali metal, find the third period, 1, 2, and 3. And the alkali metal is the first column, right? So that would be sodium. The alternative name for group 1A is the alkali metal. Okay. A halogen, which is this group right here, group 7, in the second period. So 1 and 2, that looks like it's fluorine. Okay. Yep. Then finally, a noble gas. The term noble gas sends us over here to the last column in the fourth period. So that would have to be good old krypton. 4 periods down. Okay. All right. So that's how we go about deciphering these questions here with respect to name a certain type of element or determine what the element is. Okay, this was a rehash of what we did earlier in the chapter, where you're able to determine which ones are metals, which ones are non-metals, and which ones are metalloids. Remember, metalloids are those elements that have properties of both. They have properties of metals and properties of nonmetals, and those are denoted here in green as follows. And then everything to the right, including the hydrogen far left, are nonmetals. Okay, so these are NM nonmetals, including hydrogen, and then everything in blue are labeled metals. Okay, now with that in mind, that means that all the nonmetals, given that they gain electrons, will become anions. And all the metals, given that they lose electrons, will become cations. We are going to put together the cations and the anions to make a ionic compound. CPD is shorthand for compound, which is the combination of cations plus anions, or the combination of metal ions plus the non-metal anions. Okay, those are ionic compounds. So that's why it's important that we know who's the metal, who's the non-metal. Once we know that, we can then determine, okay, what is the charge of the metal? What is the charge of the non-metal? And you might say, well, wait a minute. Earlier, I stated that these intertransition metals are unpredictable. There are a variety of charges, and that's true. But you will always know the charge of these metals 100% of the time. Everybody here has a +1. Everybody here has a +2. And then I gave you 3 more. I gave you aluminum, zinc, silver, and cadmium. Okay. Aluminum always has a +3. Zinc always has a +2. Silver always has a +1, and cadmium always has a +2. There are 16 elements, metals that you know 100% of the time what their charge will be. Okay, 16. Call those a sweet 16. And that's important to know too, because when we start naming these compounds, the fact that they have 100% constant charge determines how we name the compound. Okay. All right. Now, all the other nonmetals, starting from nitrogen and phosphorus, then down in here, these guys will have a -3, -2, -1. Okay. I'm highlighting these are the anions. Now, with that being said, do you know 100% of the time what nitride would have, what phosphide would have charge-wise? The same with oxide, sulfide, selenide, fluoride, bromide, iodide. You know 100% of the time what their charge is. They're exact all the time. I also stated earlier that when I put a compound together, I'm going to have X amount of positives, X amount of negatives to come together to give me net zero. Okay. So that means that I will always know the charge of one or the other. Okay. So I may not know if I'm dealing with, say, one of these intertransition metals like cobalt. I don't know what kind of charge they may have, but they could be combined with, say, cobalt with fluoride. So the structure you see is COCl2. Now, I don't know what the charge is for the cation because it's variable, but I do know that the fluoride always has a -1, and I know there's 2 of them. So that means that there's a total of -2 for the chloride. So I got a real simple algebraic equation. Cobalt -2 equals 0. That tells you that this cobalt has to be a +2 to cancel out the -2 from the 2 chlorides. Okay. That's what I mean. You're always going to know one or the other. You're going to know the charge of the cation, the charge of the anion, or vice versa. But before you do all that, you got to know what charge they are, what they have. Okay. Which then allows us to put them together correctly in the right ratio to right compounds. Formulas, I should say. All right. Now, the radius, atomic size, that is the distance from the nucleus to the outermost electron. Okay. So as we go down the periodic table, it makes sense, doesn't it, that we go to a different energy level, the first energy level to the second, it's a bigger diameter. So obviously the elements going down the periodic table get bigger. Okay. So I can use the periodic table to make predictions. If I want to predict the size, the radius of, let's say, oxygen with selenium, well, who do you think is bigger, O or SC? Who do you think would be bigger? Well, that would be selenium, because it is in the 4th energy level, whereas oxygen is only in the 2nd energy level. So as we go down the periodic table, the radius gets bigger. Okay. The radius of the element gets bigger. Yeah. Now, where it differs a little bit, you might anticipate now within the same period. I'm going to stop here after this slide. You would think that maybe as you go from left to right, that they will get bigger, but it doesn't. Actually, as you go across the periodic table, the radius of that element gets smaller. Okay. It gets smaller. And the reason it gets smaller is this: as you go across the periodic table, you increase the number of protons and you increase the number of electrons. And so there is more nuclear charge going on. There's more positive and negative interaction occurring. So that the results is the electrons are holding closer to each other through the radius. So they get smaller. Okay. For example, if we compare, let's say, carbon, okay, versus fluoride, well, carbon would be bigger in radius than fluoride. And that is because fluoride has 9 protons and 9 electrons, 9 positives and 9 negatives, whereas carbon only has 6 positives and 6 negative electrons, okay? With fluoride having more nuclear charge, it's pulling everybody in much tighter. And so and that's true as we go across the periodic table. And the radius gets smaller as we go across the periodic table because the nuclear charge gets bigger. The electrons get pulled in tighter, which goes along with the idea that metals and nonmetals want to not lose electrons, because as the fluorine gets smaller, because there's more nuclear force pulling in the electrons, guess what? Those electrons are going to be tougher to lose them for these nonmetals compared to the metals, where that electron is out there all by itself, and they don't have that much protons wanting to interact with, bring them in tighter. So metals want to lose those electrons, whereas the nonmetals, because of the number of protons they have in there, they have more affinity to gain electrons. They can't give up those electrons as readily. All right, sorry I took a little bit extra of your time. Let me stop it here.